Hello, I'm Jacob Merovach. I'm a DevOps engineer too at Ginkgo Bioworks and the creator of the Shepherd project. Shepherd is an internal tool used at Ginkgo to scale batch processing workflows in AWS, and I'm here to talk a little bit about how it came to be, how it works, and some of the strategy behind its implementation. I work for Ginkgo Bioworks. We're a company with a multi-billion-dollar valuation and over 300 employees. Our mission is to make biology easier to engineer, and we make organisms to spec. Most of what goes on at the company, at least before COVID, happens in the top 2 floors of the building on the left here. Our logo is on the right, which overlooks the ocean and this huge dry dock with ships pull in and out of all the time. Ginkgo Bioworks is basically genetic engineering at scale with robots. It's beyond exciting. You get to work with some of the smartest people on Earth and solve some of the most interesting and insane problems, both computationally and otherwise. It's a really inspiring place to be, and you feel this cool energy every day when you come to work. The core of everything going on is a real excitement surrounding the science we get to do. I'm a DevOps. I keep the lights on when it comes to our digital infrastructure. I build, maintain, and develop digital infrastructure. I help facilitate science, and I automate processes. Sometimes that's helping scientists do cutting-edge work, and sometimes it's automating repetitive processes to save time and man hours. By the way, there's this culture of whimsy at Ginkgo whereby a sort of fun joking around is encouraged. Mostly this turns into hundreds of different Slack emojis, but sometimes it becomes a tool that automates parts of the bubble tea ordering process. This is a real thing I made and has been dubbed by one of our founders who I didn't realize was the Slack channel I rolled it out in as TOps. That's written in Google Compute Cloud though, so we're not going to talk about it for the rest of this presentation. Working at Ginkgo at first is kind of nuts. Just because of how vast the operation deals with are, it took me a few months to sort of see how everything fit together at the company and who did what and what went where. As fast as I could, I wanted to get involved with as many things as I could get my hands on. I was learning so much and the problems I was getting to solve were really interesting. There's at least a dozen cutting edge science projects going on at any time and probably n squared that many DevOps problems you could be contributing to. My time of grabbing as many projects as I could get my hands on, I quickly became involved with a ton of different teams at Ginkgo. And as I was making my way through the teams, word spread that I was a guy who could get things done, and more importantly, it gave me insight into the classes of problems that the company was grappling with more generally. Before I get into what I recognize to be one of the biggest problems and how I was able to start to tackle it, I want to introduce 2 of Ginkgo's favorite things, scaling and automation. Both of these favorite things can be sort of nicely summed up by an internal observation referred to as Knight's Law. Tom Knight is one of the co-founders of Ginkgo. I'm going to sell him short here for the sake of time, but basically he's one of the founding fathers in synthetic biology, and he also was a pioneer in computing, which is awesome because if you work at Ginkgo, you get to walk by this guy in the hallway and marvel at the fact that not only is he real, but that people like him really exist. Ginkgo has a law in the spirit of Moore's Law called Knight's Law. Moore's Law is the observation that the number of transistors in a dense integrated circuit doubles about every 2 years. Knight's Law is the observation that the output from the Ginkgo foundry, where we produce organisms, has doubled every 6 months since 2014, while cost per output drops 50% each year. Ginkgo takes Knight's Law very seriously, and the way it achieves this is by being super innovative and also by automating everything. If you make something, the operative question is, will it scale? And the answer to that question better be yes. The general rule on DevOps at Ginkgo is that if you have to do something more than once, you should automate it. No exceptions. I was doing a bunch of things ranging from protein engineering to invoice handling to RNA analysis, and ultimately common thread began to emerge with most of these things. Basically, someone would figure out how to do a really cool analysis or process on-prem hardware, and then they wanted to scale it. Some of these things were very intensive scientific processes and our jobs that would go on for weeks at a time, act on terabyte-sized inputs data sets, and use over 300 gigabytes of RAM, and pretty much all the CPU across 64 compute cores. And others were less resource-intensive processes that just needed to rapidly scale. Almost everybody would underestimate how much they needed something to scale up front, because as a rule, if someone made something that was really cool, other teams would notice it and want to start to use it for their workflows as well. Depending on the team I was working with, there was also a large variation in skill set. Generally, there was at least one person on a team who could use Docker, and there was generally at least one person on a team that knew a programming language of some sort. Most of the time, they had at least one person with some AWS experience, but often this was something like, I've used S3 one time, or something to that effect. Most of the time, people were coming to me with stuff they had written and wanted to scale, but other times the requests were more general and were for help getting some sort of external tool or software to work with internal data, which I would then proceed to write into a container for them. Also, everyone almost universally wanted these requests to be completed immediately and for any and all inputs, outputs, and error logs associated with all jobs to be stored in perpetuity forever in some easy to access location. Over the course of a few months, I began to realize that there was a general solution to this class of problems that would allow me to rapidly turn around these sorts of requests. Broadly, the problem was around scaling processes that weren't microservices. People wanted to kick off a bunch of jobs and then go back and get outputs later, or to back-end large-scale processes for front-end API calls. If I was going to solve this problem more generally, I had to make something that was, one, accessible to anybody, irregardless of their skill and knowledge levels with the cloud and so on. A lot of these teams had different abilities, but if this was going to work for everyone, it really had to work for everyone. And it had to be usable by people who didn't have much experience and by people who had more experience and expected more functionality because of that experience. Two, it had to be rapidly deployable. Just because of the sheer number of projects people needed to scale, this had to be really fleet-footed. People wanted to be able to have multiple environments to test and deploy in, and they always wanted these things immediately. Three, it must be something that end users could use on their own. If the team is a bunch of PhDs doing cutting edge science, the last thing they're going to want me to do is muck around in their code. I was 25 for most of this project. I'm 26 now. And the last thing a group of PhDs who are among the most accomplished people in their field want to think about when something goes wrong is this the result of something I did, or is this because this kid fat-fingered something somewhere while he was mucking around in my code? You basically want to give people an easy mechanism for deploying their code into whatever is going to scale it. And four, it must scale from the get-go to potentially ridiculous levels. The common underestimation I saw was that everyone would scope out their scaling needs based on what they were going to do. But almost always, if someone made something cool, as people caught wind of it, they were going to want to use it too on other teams. So you had to account for that from the get-go. I realized I could accomplish what I wanted to through the use of a CloudFormation template that instantly made a very scalable and modular workflow to work on any sort of containerized code. My goal was to make a very friendly workflow that could be stood up almost immediately with no external dependencies in rapid order, and that any team could easily and immediately plug their container code into to rapidly scale a process. It took around 2 months of development on my part from the time I pitched and got the idea approved to when I finished it around a week before my birthday. The result of the work was an internal tool called Shepard, named after the first American to go into space, that accomplished the problem I set out to solve. As a sort of jab at Rancher, which was another tool we used frequently, which uses the terminology of herds and cattle, my tool is called Shepard and manages flocks of sheep. Shepard is a CloudFormation template and a company-made custom CLI. The architecture allows for automatic and easy execution of arbitrary container codes against uploads to an S3 bucket. Running in a standard account with no other lambdas in it, the architecture can turn over 17,500 uploads to an S3 bucket into batch jobs a minute and can queue to over 120,000 jobs simultaneously at any one time. This means that it takes a little over 57 minutes to turn 1 million uploads into AWS batch jobs. It provides options to create AWS EFS and/or high-performance AWS Lustre file systems and auto-mount them to worker containers, and has options to securely store and interact with authentication tokens and other sensitive crypto matters stored in AWS Secrets Manager. It comes with a command line interface that allows users, among other things, to easily batch out jobs, deploy new code, query existing jobs, and deploy authentication files and crypto matter to Secrets Manager, each with a single command. The whole architecture can be built or deleted in under a half hour. You can build architectures in parallel at the same time in AWS with CloudFormation. The CloudFormation template it uses is self-contained, so it requires no external dependencies like Lambda code or layers to be stored in S3 buckets beforehand. Moreover, the part of the architecture that stores container code actually builds first, so sometimes I trigger code deployment immediately after starting a build process on an architecture, and then by the time the architecture is done building in CloudFormation, I can immediately begin processing jobs. I've set up many fully completed functioning architectures in as little as 20 minutes. So even operating under standard account limits, my tool is able to provide teams at the company very easy access to some serious scaling abilities for heavy-duty workflows. Again, you can use my tool to turn 17,500 uploads to an S3 bucket into batch jobs a minute, assuming you use all of the default concurrent Lambda executions in the count, the default of which is 1,000 before you raise it via a service limit increase request. Going off this math, you can create over 1 million batch jobs from S3 uploads in an hour. Also, using some innovative code, I was able to modify batch to run essentially arbitrarily large containers, and it works on input data sets of any size. I'll get more into how I accomplish both things later in the presentation. And one of the best parts of the CloudFormation that accomplishes this is that it's all self-contained. It will run in any of the AWS accounts that Ginkgo uses without the need to upload any dependencies to an S3 bucket or anything like that beforehand. Any lambdas it runs are written to use nothing but the libraries that come with the AWS Python library, AWS Python runtime, and are short enough that they can be included as inline code in the CloudFormation. So we're going to approach how the architecture works by breaking everything down into two main components. The first, outlined in red, focuses on how Shepherd actually batches out jobs from an input, and the second, outlined in green, focuses on how more of the runtime section of Shepherd that completes tasks and outputs results works. Most of the time when you look at AWS architecture diagrams, there's a whole bunch of networking components. I wanted to de-emphasize this for the sake of decomplicating this architecture. Basically, you specify a VPC and some subnets, but there's a lot of flexibility in how you run things in Shepherd. Shepherd doesn't really care whether or not you use subnets that talk to the internet or not. If your containerized workflows need to talk to the internet, then when you run the CloudFormation, you specify subnets that accomplish this and has IP addresses set up to do so. But if you don't need to use precious networked IP space, you can specify subnets in a VPC that allow you to use unnetworked IP space. I wanted to emphasize that Shepherd in general is not pinned down to a specific type of subnet/VPC setup. So we're going to talk about why I started using S3 as an entry point. I experimented with a lot of different input interfaces for this, but it was ultimately determined that the S3 bucket was by far the best input interface, and I'd like to illustrate why with the story. I was developing an automated pipeline for a team at Ginkgo a few months ago in the pre-Shepherd era of my life. Every day I made progress developing this architecture. I'd pin the team on Slack and I'd say, great, I got this part working in AWS, and I think I'll be able to do this next bit in the following way, and so on and so on. Every time I pinged the team, they'd say something along the lines of, great, that sounds good, or that sounds like a good idea, or thanks for the update, and things of that nature. Anyhow, I finished the architecture, and when I did, we had a handoff meeting. I had some slides prepared, and I showed them where the architecture was in AWS and how they could trigger processing jobs by dropping formatted data sets into an S3 bucket. And you want to know what the first question I got asked was? Great, thanks for making this for us. How do we log into AWS? This whole time I thought I'd been designing an architecture for people who had used AWS in some capacity before, but I quickly realized that I had misread my audience. Thankfully, some other members of the DevOps team were at the meeting. We were able to sit down with the team and show them a little of how to use AWS. And basically what my team was able to do was to set up mounting the input interface S3 bucket and output S3 bucket as folders using Storage Gateway. And we told the team, if you drop your data sets in this folder at the end of the day, when you come in the next morning, the results from processing them will be in this other folder. This team had very limited AWS experience, and despite that, at the end of this hour-long meeting, they were able to use AWS to process their data sets in parallel, when previously they had been processing these data sets by hand and sequence on local hardware. The moral of this story is that this architecture can be used very effectively, even by people with almost no experience using AWS or cloud computing in general. Dragging and dropping is an interface that's intuitive enough that it can be used by everyone. As was previously stated, a job is started when a formatted data set is uploaded to the Shepherd S3 trigger bucket. A formatted data set is a zip that contains, at minimum, a file called inputs.txt that contains a JSON that specifies as many or as few key value pairs as the user would like. These input key value pairs will later become available to working containers as environment variables when it runs later. The initial input zip will also be available to a working container later on as well. Input zips can be any size and contain as much data as you would like. This upload to an S3 triggers an SQS message to be sent to an SQS queue. The SQS queue is consumed by a processing lambda, which initializes a row in an authoritative state DynamoDB that self-cleans itself of rows for completed jobs as jobs complete, and amongst other things, provides variables for command line inputs and auto-updating variables for things like job state. The processing lambda also creates a batch job and can resubmit an event to the SQS queue if a batch endpoint rejects a job due to being overwhelmed by API calls. If a poison pill message can't be handled by the Lambda job scheduler, it is moved to a dead letter queue for error analysis. As was previously stated, a job is started when a formatted data set is uploaded to the Shepherd S3 trigger bucket. A formatted data set here is defined as a zip that contains, at a minimum, a file called inputs.txt that contains a JSON that specifies as many or as few key value pairs as the user would like. These input key value pairs will become available to worker containers as environment variables when they run later, which makes it really easy to inject specific arguments into a job call. These variables are also stored in the authoritative state DynamoDB, along with the job's UUID and auto-updating metadata variables for things like job state for easy visibility. The initial input zip will also be available to a worker container later on as well, which gives jobs really easy access to data sets that you want to upload. Again, input zips can be any size and contain as much data as you would like, and we'll discuss later on how the processing Lambda handles zips that are arbitrarily large. There's a couple ways to get started with Shepherd. Ultimately, what it boils down to is that if you get a properly formatted zip file into the S3 bucket, it will turn into a batch job. There's very little concern for how that zip gets uploaded to the S3 bucket, so you have a couple of options. You can drag and drop into the S3 bucket with a console or an S3 bucket mounted to a folder using Storage Gateway. You can also use the Shepherd CLI, which has a command called batch that turns a folder of inputs into a properly formatted zip and uploads it to an S3 bucket. It also has nice options to work with assumed roles and MFA for the Boto3 calls it makes on the back end. You can use the AWS CLI to upload things to S3, and thus you can also use it to trigger jobs in Shepherd. The other thing is it's nice to be able to teach users that you can automate processes for Shepherd by automating calls to the AWS CLI or the Shepherd CLI using cron jobs and other things of that nature. The processing/schedule Lambda is compact enough that it can be stored as inline code in the CloudFormation and uses no packages that do not come with the standard Python Lambda runtime. This means that you don't have to pre-upload any Lambda code or Lambda layers to an S3 bucket to run the CloudFormation to build Lambdas. The schedule Lambda runs very consistently for any size input zip in around a few seconds. The way that the scheduler works is that it reads a select number of bytes at a fixed location from the input zip that contains information about the names of files in the input zip and the byte ranges they exist in. Then the scheduler uses that info to read out the data contained in the inputs.txt file from the zip by querying the specific byte range that contains that file. This means that the scheduler doesn't need to read the entire data set into RAM or the temporary disk space allocated to the Lambda, which allows us to run arbitrarily large data sets. Once we've read out the key value pairs from the inputs.txt file, this information along with the collision-free UUID that the Lambda computes and some metadata about the jobs regarding their status and start and stop time are put into a row in an authoritative state DynamoDB. The scheduler Lambda then triggers out a batch job and encodes, amongst other things, the same UUID to the specific runtime environment of the job. This allows for the worker container to efficiently query the aforementioned DynamoDB and get the inputs of the inputs.txt along with the other job metadata, and then pass the key value pairs for that row along as environment variables to the worker container. It also allows for really nice tracking of logs to see the path from zip upload to Lambda call to batch stop completion to output path. Being able to batch out jobs and then query a centralized location to find out about the status of those jobs is incredibly useful. Each Shepherd architecture automatically gets a DynamoDB created by CloudFormation, and it uses this database to store key value pairs for variables associated with the run, and it also stores auto-updating metadata variables that talk about things like run start and stop time and job status. We'll get into how these variables auto-update later. You can use a query command with the Shepherd CLI to directly query this DynamoDB to find the status of jobs. When a job finishes a TTL, that's time to live variable, gets auto-updated from thousands of years into the future to the present time. This causes the database to auto-clean itself and delete rows for finished jobs, which allows the database to manage itself and not fill up with millions of lines when completing jobs. The nature of DynamoDB also lends itself really well to getting hammered on by thousands of Lambda executions in containers simultaneously, provided you configure it properly. Now we're going to talk about the part of Shepherd that's more associated with the runtime architecture. Shepherd can run any variety of container and does so on a managed batch fleet of spot or dedicated EC2 instances. You get to pick which of these you want in the drop-down menu when you build the CloudFormation for Shepherd. And it takes inputs from an S3 bucket and deposits outputs to another S3 bucket automatically. It also uses a secrets manager storage to securely reconstitute authorization files and tokens at runtime, and communicates with the authoritative state DynamoDB to update job metadata variables in real time and injects user-specified environment variables into containerized workflows. In the event of a crash, Shepherd also automatically deposits a zip with error log data into a log S3 bucket. One of the driving principles behind the architecture was to achieve control over how users were able to interact with the architecture, and that was achieved through the use of Docker and Docker. Basically, instead of batch starting my container, batch starts a container that runs a script that I call universal worker code, and this code starts the user's container. To do this, you basically have to build a Docker D&D container that can run a Python script, and then you have to have that container also build the user's payload container. D&D stands for Docker and Docker, which is a Docker container that can also run Docker. You use Docker and Docker by passing in /var/run/docker.sock as a volume mount to /var/run/docker.sock in the D&D container. I first do this on the host computer when building a container for deployment. However, if you then try to run a container you built on the host PC in the cloud by passing in /var/run/docker.sock as a volume mount from an EC2 instance, you'll get an error because the new Docker daemon on the EC2 instance has no knowledge of the container you built on your deployment machine. The way to get around this is you use /var/run/docker.sock from the host instance to allow your Docker D&D container to build the user's container. And then you turn that container into a .tar file inside the worker container. Then when you go to run this in the cloud, you pass in the Docker daemon as a volume mount again. And this time you're using the EC2 instance's Docker daemon. And then you use Docker to reconstitute the user's payload container from the tar file and call it from the universal worker code. This whole process sounds complicated, and it is, but the process of turning a folder containing materials for making a Docker container into a nested container like the one I described is now a one-line command call using Shepherd CLI. If you were AWS and you are calling stuff behind the scenes, anyhow, there would be better ways to do this, but alas, I am but a lowly DevOps engineer too, and so this is the only way I could see to achieve what I wanted to achieve. That said, it works very reliably. Anyhow, the worker code takes care of things like fetching the input zip to the worker container, updating job metadata variables, securely reconstituting authorization files and cryptomatter to locally encrypted EBS volumes on the EC2 instances made available to the worker containers via volume mounts, uploading results, and making calls to the Docker container with the appropriate volume mounts and ulimit values. It all runs behind the scenes, and the latest up-to-date version of the worker code is fetched automatically by users when they use the Shepherd CLI's deploy command to automatically build and push the container to ECR. Reproducibility in bioinformatics is often a problem. There's so many variables that can affect the results coming out of a workflow that it helps to version workflows appropriately so you can track what you did to get an output as best as possible. ECR, which is what backend storage for containers for Shepherd, automatically versions your containerized workloads that you upload to it. This allows you to very easily go through CloudWatch logs and determine what version of a workload you use to get a certain output, and helps nail down some of the reproducibility issues we commonly run into in bioinformatics. Every Shepherd architecture gets provisioned with a secrets manager store that stores key value pairs in which the key is the name of a file and the value is a base 64 string represent the file contents. At runtime, the files stored in Secrets Manager are securely reconstituted back into their original forms, i.e. into the files represented by the name and the base 64 string pairs by the universal worker code and made accessible to the underlying worker containers in a secure manner by storing these reconstituted authorization files in UUID folders on encrypted EBS volumes on the host instances running jobs that then go away at the end of jobs as they complete or error out. Any reconstituted secrets will be located in the path specified by the environmental called root input name in a folder called secrets, which sits in the encrypted EBS volume used by the host instance for its root file system. This is made accessible to the worker containers via volume mount passed into the payload containers by the universal worker code that allows access and storage onto the encrypted EBS volumes AWS batches EC2 instances use. All of the mounting of file systems to the host EC2 instances, which are then passed to the worker containers as volume mounts, is all taken care of by launch templates that are auto-created by the CloudFormation. The launch templates also acts on the variables declared in the original CloudFormation template to raise the maximum number of files allowed open to a user specified number that can be up to a maximum of 1,048,576 or 1024 squared files. The launch template also allows for the spinning up of batch instances with arbitrarily large EBS volumes and modifies the storage space allowed for the storage of Docker containers on the EC2 instances. This allows for the easy spinning up from the CloudFormation template of instances by batch that can run arbitrarily large containers and have arbitrarily large root file systems. For each file system you choose to spin up, and you get a choice of EFS and or Lustre when you start using CloudFormation, you get two mounts. One volume mount is a read-only mount for the whole file system, and the other is a folder you're allowed to read and write to. The folder has a collision-free UUID name and goes away at the end of a run, either due to an error or a successful completion. And this is managed by the Universal Worker Code. When you choose to spin up a Lustre file system, you can also specify whether or not you want to create a new S3 bucket or use an existing one using the CloudFormation template. There's a dropdown for it I put in. If you pick an existing S3 bucket, the Lustre file system will import all of the data in the S3 bucket when it boots. And this data will all become available to the worker containers via the read-only mount that has accessibility to the entire file system. You also get another mount, which is to a folder on the EBS volume for the root file system used by the host EC2 instance. This folder is only available to the specific worker container and contains the original input zip that was used to trigger its job, and also any circuits that were deployed to Secrets Manager for the architecture. If there are an EFS or Lustre file system available, the input zips will be fetched there instead, so you can run jobs on larger data sets than would maybe fit on your EBS volumes. However, secrets will only ever be reconstituted on the root file system mount, the logic being that we would never want to put crypto matter any place that wasn't encrypted or onto a shared file system. So I'd like to show an example of how easy it is to code something on Shepherd by walking through the code I use for testing. Let's say I had a directory that contained a dockerfile.txt as seen on the left. And in the same directory, I had a testing code.py file as seen on the right, which is just in Python. If I ran shepherd CLI deploy on the aforementioned directory, this code would be live when the operation finished. What my code would do is detect if there was a Lustre file system and or EFS provision for this architecture. And if there was, it would write a 2 GB file of zeros to the designated output path for either. Uploads to the designated output paths automatically get uploaded to the output S3 bucket upon the completion of a job. This means that if there was a Lustre file system provision for this architecture, it would upload a file to the designated output location for Lustre. And then upon completion of the job, this output would automatically be uploaded to the designated output S3 bucket for this architecture. And if there was an EFS file system provision for this architecture, it would upload a file to the designated output location for EFS. And then upon completion of the job, this output would also automatically be uploaded to the designated output S3 bucket for this architecture. Also, both of those would be written to UUID folders that would go away at the end of jobs, either due to error or completion. It would also print out the value for the environment variable named test in CloudWatch. You can see that while it might seem complicated from an architecture perspective, it's easy to write code to make a highly scalable workflow that leverages services like EFS and Lustre in a totally safe way. So let's see how this would react to a real-life input. So let's say I ran a zip into Shepherd that contained an inputs.txt file as seen above. There's two variables designated in that JSON. One is a variable called test, which is a string that says, this will become the value associated with an environment variable named test. If we remember what the code in the last slide is going to do, it's going to print this out in CloudWatch. And if we look at the CloudWatch logs for the run, we see that this is indeed the case as to what happened. There's another variable called tag, which is what is called a reserved variable in Shepherd. Designating this variable allows you to append a prefix to outputs generated by a run. I ran this workload through an architecture for which EFS was provisioned, but not Lustre. So you can see a single output was uploaded to EFS, but not to Lustre, which it detected did not exist, and is created with a prefix equivalent to the value designated to tag, which in this case was, this will become a prefix for outputs, which we see at the start of the name for our output in S3. The command line tool that comes with Shepherd uses the credentials provided by the AWS CLI and supports assuming role using cross-account roles, using environment variable stored credentials, as is the case for roles attached to EC2 instances, assuming role using MFA, and using profiles and roles to store common variables. The CLI allows for the creation, storage, and setting of profiles, which are collections of variables with a given name that become defaults when activated. You can set a profile for each of your managed architectures, which allows you to rapidly and easily sort through and manage your architectures. The CLI also allows for the setting of roles, which uses the STS service in AWS to assume role with or without MFA, and then attaches the role variables, provided the command is successful, as default credentials with which to execute commands. The CLI has a ton of commands, but the ones I'd like to focus on describing are the deploy, secretify, batch, query, and retrieve commands. So batch is a command that looks at a directory and makes sure it's properly formatted to contain everything it needs to trigger a job when it's uploaded to S3. And if it does, it zips the directory and uploads that zip to the trigger S3 bucket architecture for an architecture. Uploading a zip to the trigger S3 bucket via the batch command will trigger a job to run. Deploy is a command that looks at a directory, and provided it contains the materials to build the Docker container, it builds a nested Docker container using the directory to build a nested Docker container inside our universal worker container, which contains our universal worker code that is in turn used to call the nested payload container. The CLI is set to use cached versions of the latest worker code to build a worker container that will contain the payload container, provided it cannot reach our local server to fetch the newest version of the worker code. Secretify is a command that takes the directory as an input and turns all the files into base 64 strings that are then uploaded to AWS Secrets Manager as key value pairs of the form, where the key is the name of the file and the value is the file content as a base 64 string. These files are securely reconstituted back into the original forms on runtime by the universal worker code and are accessible to the underlying worker containers in a secure manner by storing these reconstituted authorization files in UUID folders on encrypted EBS volumes on the host instances running jobs. Query is a command that prints out all the lines in a DynamoDB for an architecture, therein providing the person running the command with the latest updates on all of the jobs still being run or that have recently finished. Metadata regarding job status for running jobs is also updated by the universal worker code, so you can see these updated in real time if you keep on querying jobs. Retrieve is a command that fetches files from an output S3 bucket for an architecture to a local directory on a person's computer. The command is set up to only fetch diffs from the S3 bucket, so it will not attempt to fetch outputs that already exist in the local directory the command is set to download to. So we're going to go into some creative applications for how you could use Shepherd. So a very common problem in genomics involves processing FASTQ data sets from an online database, such as the National Institute of Health's SRA database. To download data sets like this, you'd want containers operating on a networked instance that can get to the internet. However, if you have limited IP space in your account, which is often the case, it would often allow for much more rapid processing if you could decouple the data set collection and processing steps from one another. A great solution to this problem would be to use two Shepherd architectures that are linked to one another. You'd want the first architecture to be networked so that it could download files from the online database, and you'd want the second architecture to use a non-networked subnet, which will allow for the spinning up of as many instances as you can until you hit your service limits. The first architecture would contain AWS access keys and a secrets manager that would allow it to dispatch jobs securely to the second architecture. When you submit a job to the first architecture, which is networked, it runs a job that collects the data set and submits it to the second architecture for processing, which is not networked, using the AWS access keys and the secrets manager to access the input S3 bucket of the second architecture. The idea here is that while you're able to spin up fewer EC2 instances in the first architecture, which has to use networked IP space, the jobs performed there to fetch data execute in a shorter time than the processing jobs on the second architecture, which does not have to use networked IP space, where you can spin up very large numbers of EC2 instances comfortably. This allows for the decoupling of the download and processing aspects of a workflow across two architectures and allows the subprocesses to scale up or down independently of one another. This frees your processing containers from having to use precious networked IP space in a subnet and allows for the mass processing of data sets from an online location using non-networked compute resources. Another thing you could do is, since Shepherd runs Docker and Docker, and actually you're able to pass the Docker daemon as a volume mount, not only to a container inside a container, but also to a container inside a container inside a container. This means that theoretically you can use Shepherd to do automated Docker builds on AWS Batch. If you're dissatisfied with the amount of time it takes to push a container to ECR from a local machine, you could build a Shepherd architecture with appropriate permissions stored in Secrets Manager to push to destination ECR repos that can build and push your containers for you. It seems like kind of overkill, but you can pretty much set up one Shepherd architecture that builds and pushes containers to ECR and effectively cover the Docker builds for your whole organization. So we're going to get a little bit into some planned usage for Shepherd at Ginkgo. So a more senior DevOps engineer than myself estimated that Shepherd could be used to automate around 60 to 70% of the workflows being done by scientists at Ginkgo currently. It's hoped that the modular and rapid deployment abilities of Shepherd lend itself well to the sort of fast-paced, rapidly changing analyses that Ginkgo tends to focus on. That said, the remaining 30 to 40% of workflows that Shepherd can't automate are mostly microservices. And in that case, it's more like shouldn't automate rather than couldn't. Shepherd allows you to specify in the input template a number of inputs that allow for the provisioning of static EC2 instances that just wait around the clock for jobs to come in. This could function as a sort of poor substitute for some microservice functions if you wanted it to, but it would be an ill-suited substitute. So in regards to future work on Shepherd, I've gotten a ticket made to open source Shepherd, and the powers that be have approved a request to open source the code. So as soon as my PMs let me move this into a sprint, it will be accessible to everyone. I'll be around to offer support to the open source version of this as my work schedule permits, and I'm also planning to roll out a few more upgrades. These will include things like the addition of an API gateway endpoint that will allow for the batching out of jobs without an S3 upload, which should allow for much more rapid batching out of jobs that don't need to act on an input data set, for which the S3 upload is a functional, although kind of a necessary trigger mechanism that's slightly slower than it could be in an optimal world. So there's two more projects that are similar to Shepherd that I want to work on and I have more or less mapped out in my head. The first would be a nigh identical version of Shepherd that uses AWS Parallel Cluster instead of AWS Batch. So you get some of the ease of use of Shepherd with the ability to run more conventional HPC workloads on clusters. The second project would be something similar to Shepherd in spirit, but for microservices. Shepherd can sort of be used for microservice workloads, but it's really more for batch jobs, and you should be using microservice workloads for building small, highly scalable services that applications can use. I'd like to make a very accessible microservices workflow that would allow users to easily stand up a highly scalable microservices architecture to run their code and provides a lot of the easy to use capabilities of Shepherds with things like easy deployment, debugging, and usage. I think this could be accomplished pretty easily through architectures using services like ECS and API Gateway that are based off some of the design principles outlined in AWS's white paper on microservices, which I really thought was a great white paper with a ton of good insights. Shepherd as a project, though, really revolves around a larger concept of making the cloud easier to use, which I think is something that can be sort of explained using certain aspects of Python. I was having a conversation with a coworker, and he asked if anyone my age, I'm 26 now, even knew how to write buffers anymore, or if I could write a buffer, because he felt that this was something that younger people weren't learning about because Python libraries took care of this behind the scenes a lot. I told him that I did, but in general, I didn't think this was a bad thing. I don't think that if people had to write their own buffers, that more people would be using buffers out there. Sure, you can write your, you can probably write your own buffer that's faster in C++ than a canned Python library would, but buffers as a tool in general are now far more accessible to people because libraries take care of this for them. People have flocked to Python because it makes so many tools that you'd have to implement or figure out yourself easily accessible to everybody. It's not the fastest language in the world, but it is one of the easiest to use, and I think that's been key to its success as a language. Because Python makes things easy to use, more people end up using those things, and more people end up using Python. I think AWS and the cloud in general can learn a lot from this. There are a few patterns that companies across the world are re-implementing over and over again in the cloud. Prime examples of this would be batch workflows and microservices. If you make really easy to use versions of these patterns that have easy integrations to AWS services, not only will people use these AWS services you have integrations with more, but they'll use AWS in general more. And then, like with Python, once you get a critical mass of people building on your system, you'll start to see really intricate, creative, and useless things emerge, like Keras or NumPy have on Python. I don't know what the equivalent of Keras would be in AWS, but I'd be excited to see it. if AWS was to implement some sort of officially supported version of my framework, or even just take the concept behind it of easy to use self-contained architectures and run with it, I would die a happy man. I think it would do great things for the cloud, for science, and for the customers of AWS. Thank you for listening to my presentation. I'm Jacob Merovach, DevOps Engineer 2 from Ginkgo Bioworks, and I am happy I got the chance to talk with you today.